Hello guys, you're welcome again to my YouTube channel. If you are new here, click on the subscribe button, and if you are old here, thanks for coming back again. We want to talk about some topic on fluid dynamics or fluid mechanics. So we were talking about laminar flow and then turbulent flow with the Poiseuille's equation. So we'll talk about maybe the applications of all this. So now we're going to start with the laminar flow. So when you say laminar flow, what does it mean? So now we know that materials that can flow or matters that can flow, they are called fluid. So when you say fluid, fluid is talking about materials or matters that can flow like air and liquids. So that is fluid. So now when we say we have laminar flow takes place in a cylindrical pipe when fluid is passing in a cylindrical pipe. So we want to consider how the property of the flow. So suppose we have a cylindrical pipe in this form. So now this is the pipe. So a laminar flow is a flow of fluid along this pipe in a slow motion, that is one, and then the velocities of the layers of the liquid or the fluid is what uniform, and the direction is also uniform. So let's take for instance, we talk about the fluid flowing like this. So this layer goes, then the upper layer goes too. So they go with slow speed and then steadily. So the direction of laminar flow is uniform and the speed is slow. So this is one property of laminar flow. So when we have the velocity of each layers of the liquid, each particles of the fluid, they move slowly and uniformly, and the direction is uniform. So now this is laminar flow. Laminar flow obeys the Poiseuille's law, or you call it the Poiseuille's equation. So this obeys it. We are going to talk about the Poiseuille's equation or Poiseuille's law after we finish exhausting what laminar flow and turbulent flow is. So if someone is to ask you about laminar flow, you just tell them it is the motion, or it is the flow of fluid through a pipe with velocity is uniform and alongside with the direction. So the direction is also uniform. So now let us talk about the turbulent flow. For turbulent flow, what happens is the motion is not uniform at all. So, and it takes place with high speed. So you see particles moving like this, crossing each other's paths. You get, so this is an example of a turbulent flow. And we can experience this when fluid is moving rapidly and randomly. So the particles of the fluid are moving randomly and their velocities is not uniform. It's different from one another, and the velocities cross each other's paths, and at the same time they move with a faster speed. So, and turbulent flow does not obey the Poiseuille's law. So now, what is Poiseuille's law and what is the significance of the law? We have the significance of the law in a lot of engineering field and also in medical field. So let us take a look at the Poiseuille's law first, so then we talk about it. So in this pipe we're talking about now, I think we're able to differentiate between a laminar and a turbulent flow. Once we're able to differentiate between the laminar and turbulent flow, we want to talk about the Poiseuille's law. So this law is significant only for laminar flow, because I told you turbulent flow does not obey it. So, but let's talk about the law. Now, one thing we need to understand is that this pipe, we have a cross-section area. Cross-sectional area is the area of the face of the pipe, so which you can also call this. It's in form of a circle, so this is the radius. Okay, so now when the fluid is flowing within this pipe, what Poiseuille's law is telling us, is trying to tell us, is that the flow rate, when we say flow rate, the volume flow rate is proportional to the fourth power of the radius. So when we say the flow rate, the rate at which the fluid flows with time. So that's, when we talk about the volumetric flow rate, we talk about how the volumes of the liquid flows across the pipe. So when we say volumetric flow rate, this is the cross-sectional area of the pipe and the fluid flows across. So then the volume of the unit volume of the fluid, when we say unit volume, that is the area. Don't forget, this is a cylinder, so the area of the cylinder is pi r squared h. So per unit length across the pipe, that's the volume. So when we say volumetric flow rate, that is the volume that flows per unit time. That is the volumetric flow rate. So if that is Q, volumetric flow rate is going to be a change in volume over change in time. This is volumetric flow rate. So now the volumetric flow rate across this pipe is proportional. So Q is proportional to the fourth power of the radius. So this is what the Poiseuille's law is talking about. And this is only applicable. This law is applicable to laminar flows, because turbulent flow, you cannot apply this law there because it does not obey the Poiseuille's law. Now, having this, we need to introduce a constant. So then we have Q equals, so we have Q equals K multiplied by the fourth power of the radius of the pipe. So this is just Poiseuille's law. So now, the flow rate does not depend on this alone. This constant has a value. So and the value is pi multiplied by change in pressure all over the 8 multiplied by coefficient of viscosity multiplied by the length. So now let's pick two areas here. Okay, from here to here we have a length L. So now between this point and this point we have a volumetric flow rate which is proportional to the fourth power of the radius, and at the same time this change in P will be the change in pressure at the the top end of the pipe and the bottom end of the pipe. So let's assume the fluid flows in through this point and the fluid flows out through this point. So we assume that the pressure here, that's pressure here, is different from the pressure here. So this change in P represents the pressure difference between the ends of the pipe. So if this is the pressure difference, we can use, it shows that this formula can also be used to calculate the pressure difference between both ends of the pipe. So then we have this, and this is coefficient of viscosity. So this is length, a given length. And if you're talking about this point and this point, the length will extend up to this point. So then this pi is just a constant. So if I substitute this into this, I'll be having Q equals pi, change in P r raised to the power 4 over 8 multiplied by the coefficient of viscosity multiplied by length. So don't forget that this change in P is it has to do with this is pressure P. So it has to do with a change in pressure on both ends. So we can write that as Q equals changing pi into PB minus PA multiplied by r squared over 8 multiplied by the coefficient of viscosity times this. So now at the same time I told you Q is flow rate, the volumetric flow rate. So then we can substitute that here and have this equation, change in V over change in T, that's the flow rate, equals pi into PB minus PA, which you can just easily write as change in P multiplied by r raised to the power 4 all over 8 multiplied by this. So this is Poiseuille's equation. What is the significance of this equation? It is applied in a lot of engineering fields, and then at the same time, when it comes to the life science, I'm talking about biology or medical, We could use this to calculate the change in pressure, or this, let's say, the flow rate. We can use this Poiseuille's equation to calculate the blood flow rate in arteries and veins. So knowing the flow rates, the blood flow rates in arteries and veins, it could help us to understand blood pressure, and at the same time help us to understand cardiovascular health. So that is one of the significance of Poiseuille's equation that is not really common, but we have a varieties of application of it in engineering field. However, when we're talking about this laminar flow and Poiseuille's law, it is applicable for incompressible fluids like water. So water is incompressible fluid, so when they pass across the pipe, the applies that their flow rate is proportional to the fourth power of the radius of the pipe. So I think we're able to explain the laminar flow and the turbulent flow as requested by a particular subscriber of this channel. Thanks for watching, and please subscribe to the channel and share the video. Thank you.